Piping for hydronic systems has been taught for decades. The principles remain the same, but changes in technology permit new opportunities to save first cost and reduce energy consumption. Upon completion of this training, one should be able to compare pipe sizing methods, understand the impact of pipe sizing on system performance, apply ASHRAE Standard 90.1 to pipe sizing, understand how variable volume, variable speed pumping influences pipe sizing, and utilize life cycle cost economics to justify the use of the Magna 3 in both new and renovated systems. As we move through the content of this training, we'll cover the following topics: pipe sizing considerations, pipe sizing methods, work through a pipe sizing example, and discuss pump and energy costs as they relate to pipe sizing. This training presentation has been developed to address the need to save energy in buildings. To date, much of the focus of efficiency savings has been on individual system components such as motors and pumps. This effort has been important and successful, but there are limitations as to how much more efficient individual components can become. The next step towards optimizing efficiency need to focus on system operation, how all of the pieces of the system work together. Hydronic piping is not new and designers have been sizing it for decades, but little attention has been given as to how much this pipe sizing influences the overall system performance. Even more interesting is that many designers do not even know why they size the piping the way they do, besides they have always done it that way. We'll cover the background of why we select pipe the way we do, and what needs to be considered as we move forward with better and more efficient designs. All of these items, material type, first cost, pump energy cost, internal pipe erosion, noise, and budget influence pipe sizing procedure, but rarely are they all considered. The first item we'll consider is the pipe material. There are many different pipe materials used in hydronic systems, but the two most common include copper and steel. For this reason, we'll limit our discussion to only these two materials, although the principles could apply to any material. It is important to clarify that pipe of different materials, although the same nominal size, do not have the same inside diameter. The inside diameter influences the performance because it impacts the free area of the pipe. The smaller the ID, the greater the velocity, and in turn the higher the friction loss or head. For this presentation, we'll focus on the most common pipe types used in commercial design: copper type L and steel schedule 40. The 40 in the L reference the wall thickness of the pipe. As illustrated here, the 2-inch copper pipe has a smaller inside diameter than the 2-inch steel pipe. As we can see, the nominal 2-inch copper has an internal ID of 1.985 inches, and the nominal 2-inch steel pipe has an ID of 2.067 inches. The common methods of sizing pipe are usually the constant friction rate or velocity. When applying either of these methods, there are rules of thumb or commonly applied values used to set limits when making the decision. The constant friction rate as the pipe sizing method does just as the name implies, sizing the pipe to maintain a constant friction. The friction rate ranges from 1 foot of head per 100 feet of pipe to 4 feet of head per 100 feet of pipe length. 2.5 feet per 100 feet is the value used on average per the ASHRAE handbook, unless the pipe diameters exceed 2 inches, in which case the friction loss is increased to 4 foot per 100 feet of pipe. In practice, designers utilize values anywhere within this range. The second common method of pipe sizing is using maximum velocity. Commonly, designers use a max value of 4 foot per second for pipes 2 inches or below, and 8 foot per second when pipe sizes exceed 2 inches. But there is not a standard that defines the values used. The primary reason velocity is limited is to prevent noise and internal erosion of the pipe. The table here from ASHRAE Fundamentals reinforces these velocities as being acceptable values. One thing worth noting is that the most recent research, 1976, on this topic is long before many of the technologies applied in our hydronic systems existed, such as variable flow, variable volume systems. Closed-loop systems can exceed these velocities since the air that does most of the erosion damage and creates the noise is removed from the system. This being said, the absolute highest acceptable velocity is 15 foot per second. The piping material selected will also influence the acceptable water velocity. Copper pipe velocity limits have been researched by Copper Development Association and are published in the Copper Tube Handbook. It's important for a designer to be sensitive to information published by many different sources, and as noted here, water temperature can be an influencing factor. We can see that for copper tubing, according to Copper Tube Handbook, that for chilled water applications, the maximum velocity is 8 foot per second. We can see that for hot water applications less than 140 degrees, that a maximum of 5 foot per second velocity. And for hot water applications over 140 degrees Fahrenheit, that they recommend a maximum velocity of 3 foot per second. Also, in very small pipe size, the maximum velocity should be reduced because craftsmanship and abrupt changes in flow direction will have greater impact. Pipe sizing tables can also be used to size pipe. This table, published in ASHRAE Fundamentals, is for steel Schedule 40 pipe. On this table, you'll find the flow on the horizontal axis at the bottom of the chart. You'll find the head loss on the vertical axis to the left of the chart. And you'll find the pipe size on the diagonal from the lower left to the upper right on the chart, and the velocity on the diagonal axis from the upper left to the lower right on this chart. If using the constant friction rate method for sizing, you look first to the vertical axis and reference the rate that will be used. In this case, we are indicating the 2.5 foot per 100 feet rate that is shown by the blue line. A designer could also choose to use a higher head loss value at 4 foot per 100 feet as represented by the green line. If maximum velocity is the preferred method, this can also be located on this chart. For this example, the red line highlights a velocity equal to 4 foot per second. Each of the correlating values to values of 2.5 foot per 100 feet of pipe, 4 feet per 100 feet of pipe, and 4 foot per second can then be looked at to see where they cross a specific pipe size. From there, the maximum flow rate can then be determined. The 1-inch pipe has been identified in the yellow, and the orange arrows to the horizontal axis of gallons per minute to be established. 2.5 foot per 100 feet of pipe would be 5.5 gallons per minute. 4 feet per 100 feet of pipe would be 7 gallons per minute, and a velocity of 4 foot per second would be at 11 gallons per minute. Now take just a moment to overlook all the information on this slide. This same process can be done for all pipe sizes, and a chart can then be created. ASHRAE also publishes tables for copper pipe. When selecting pipe sizes, one must use the chart that correlates the correct material, since they are not all the same, to account for the fact that the inside diameters are different. If we look for the same intersections of lines as we did on the steel chart, we can create a copper sizing chart. This then would be a created copper type L pipe sizing chart. What is interesting is looking at the charts side by side. You'll notice that the gallon per minute values for the pipe sizes are very similar. This is a result of using the ASHRAE chart that correlates to the corresponding pipe material. Noise has been mentioned a couple of times as being a factor in pipe sizing. Most hydronic systems are closed-loop systems. Therefore, this is not a significant concern since the air that is typically causing the noise has been removed from the system. When this is an issue, maximum velocity is difficult to determine due to the many variables including pipe insulation, numbers of turns, fittings, valves, and partial flow. As long as velocity is below 10 foot per second, erosion is not a significant concern. The limits can be higher than 10 foot per second if the operational hours per year is not high. Aging is another issue that can affect the free area and the friction loss in a hydronic system. Recognizing that this is an issue, it is fair to say that it is typically ignored because it is unpredictable and research has not been done to establish values that should be used. Aging is typically only addressed in open systems if accounted for at all. Evaluation of internal pipe condition is best practice in a retrofit situation, since the water treatment during the life of the system is unknown. Either a section or two should be removed and examined, or a pressure drop analysis should be conducted on the system. Having had some exposure to pipe sizing methods, now let's apply them to an example of a closed-loop chilled water system in a building. The example is a 4-story office building located in Houston, Texas. The building cooling is accomplished with an air-cooled chiller serving fan coil units at the zone level. The office basement level is broken into 6 different zones, plus a mechanical room that houses the pumps. Each zone has its own thermostat connected to a fan coil unit, as is the case on all of the floors. The main floor is broken into smaller zones than the basement, since these spaces are primarily occupied spaces compared to the basement that is mostly utility-type space use. And for this example, the second and third floor layout and zoning are identical. The total peak load for the building is just less than 40 tons of cooling. 81 gallons per minute of chilled water will be delivered to the fan coil units located within each zone. This diagram represents the riser diagram of the piping to each of the floors of the building. In addition to the gallons per minute being listed, the associated pipe size is also indicated. The pipe is sized using the constant friction rate method, using the value of 2.5 feet of head per 100 foot of run. You'll notice that the material choice has no impact on the nominal pipe size selected in this situation. Each of the floors of the building are shown with hatch boxes representing the fan coil units, and the chilled water main routed to each of the units. The number is the unit reference number, and the value in the parentheses is the unit gallons per minute. The return piping is not shown to simplify the plan for the purpose of this example. The piping is based on the flow in gallons per minute that will be carried to serve the units downstream. The pipe in the furthest unit will only need to carry 0.9 gallons per minute to this unit. Therefore, the pipe size is small, only 1/2 inch. The only discrepancy between pipe sizes due to material selection is highlighted by a blue circle. Completing the same pipe sizing exercise for the main floor, it can be seen that again there is only one minor difference in line size between copper and steel. This is further evident in the second and third floor piping. This diagram indicates the differences in the second floor piping system. And once again, the discrepancies in the pipe dimensions are listed in the blue circles. The third floor pipe sizing is different than that for the second floor, even though broken into the same number of zones. The difference is attributed to the roof load that is seen only by the top floor. We have just seen that the material selected has a negligible impact on the size of the pipe selected. So now let's consider the different sizing methodologies. When we look at the riser diagram again, we see that depending on the friction value used and the maximum accepted velocity, the pipe size can vary. Based on this diagram, we can see that at our basement level, it may start with 1¼ inch pipe from our riser, but be reduced down to a 1 inch pipe by the end of the run. With our main floor, it may start with a 2 inch pipe, but reduced down to a 1½ inch pipe at the end of our run. On the second floor as well, it could begin with a 2 inch pipe and be reduced to a 1½ inch pipe by the end of the run. And the same could be said for our third floor, would start with a 2 inch pipe, but be reduced to a 1½ inch pipe by the end of our run. This variance in pipe size applies to the individual floors as well as the riser diagram. This variance in pipe size also applies to the main floor. As well as the second and third floor. We have spent quite a bit of time talking about pipe sizing, but what is most important to this discussion is how the pipe sizing is related to the energy consumed by the system and ultimately the pump energy costs. The pump must work to overcome the resistance in the system that occurs as a result of the piping layout, the equipment applied, and the pipe sizing. The work or energy exerted is then converted into cost depending on the price of energy, the efficiency in the operation of the system, pump control and efficiency, and the hours of operation. The pump selected must exert enough energy to overcome the pressure drop or the head imposed by the critical circuit. The critical circuit is the water path that sees the greatest pressure drop. This is often the longest run or the path with the piece of equipment that imposes a large pressure drop. Some pressure drops are attained from manufacturer literature such as coils and valves, whereas fitting and piping resistance can be calculated using the ASHRAE tables. Pipe resistance is determined using the same sizing tables used before from the ASHRAE fundamentals. What is the pressure loss imposed by 50 feet of 3-inch Schedule 40 pipe with 81 gallons per minute of water flow? First, find the two variables that are given. The yellow line for the 3-inch pipe and the green line for the 81 gallons per minute. Where these two lines intersect, a horizontal line can be drawn to determine head loss. This is represented on this diagram by the orange line listed here. The head loss value is 1.5 feet of head per 100 feet of pipe length. The head loss as a result of 50 feet of pipe length is calculated to be half that amount, or 0.75 feet of head. This process needs to be done for all the straight lengths of pipe in the critical circuit, and then those values are totaled. In addition to the straight length of pipe in the critical circuit, fittings must also be considered since they also create resistance. The resistance for a fitting is given in terms of equivalent length of pipe that can then be converted to head as done with the straight pipe length. The tables for equivalent length are based on the velocity, pipe size, and the type of fitting. Take just a moment to study the information shown on these charts. Now let's calculate our pipe resistance. Let's first consider the velocity. Staying with our example of a 3-inch pipe distributing 81 gallons per minute of chilled water, we can determine the velocity using our pipe sizing chart. Again, locate the two variables that are given. The yellow line for the 3-inch pipe and the green line for the 81 gallons per minute. Where these two lines intersect, the velocity can be determined by the red line shown here. For this example, the velocity is approximately 3.3 feet per second. The equivalent length table can now be referenced to determine the loss associated with the fitting. We use our velocity calculation of 3.3 feet per second, where velocity is located on the first column. We then look for the column associated with the pipe size of 3 inches. We can now read from the table that the equivalent length is approximately 8.1 feet for a 90-degree elbow. Now, if the fitting is something other than a 90-degree elbow, a correction multiplier should be applied. What if we used a 45-degree elbow? Well, then we'd look to the chart and see that a 45-degree elbow uses a multiplier of 0.7. We then use our multiplier times the 8.1 This means that the resistance of one 45-degree 3-inch elbow is equal to 5.7 feet of straight 3-inch pipe. As we can see, the pressure drop calculation to determine system head can be very time-consuming. For this reason, the process is often simplified by the designer. If the pipe had been sized using the limit of 2.5 feet per 100 feet, this value is then applied to the entire pipe length. This will result in overestimating the head in many situations, since much of the pipe was not sized at the upper limit of what is acceptable. The other time-saving practice is to apply a multiplier such as 1.5 to the total length to account for the fittings rather than calculating the loss of each fitting independently. The result of this lack of precision during the design phase often generates a head value that is overestimated and in turn a pump that is oversized. ASHRAE Standard 90.1 has a section under the prescriptive path requirements that addresses pipe sizing. This table defines the maximum flow rate for different sizes of pipe. The maximum gallons per minute is dependent on operating hours and system operation in addition to pipe size. The reason this is included in Standard 90.1 is because undersized piping results in additional pump energy consumption to overcome the extra head resulting from increased friction. The table includes operating hours because 90.1 requires all requirements to be economically justifiable, meaning that the energy saving must pay for the increased first cost over the life of the system. A couple of clarification items related to this table are that these limits are only applicable to the chilled water and condenser water systems. The table primarily focuses on energy, not the issues of erosion or noise, since the pipe sizes affected begin at 2.5 inches. The piping being considered is primarily distribution piping that will be located outside the sound-sensitive areas and likely be insulated. Hot water is not included because the pipe size can be smaller since the heat of the pump is transferred to the water. To then apply Standard 90.1 limits to our example, we need to know the hours of operation. Our 4-story office building peak load is nearly 40 tons with 4,567 total cooling hours. Now please take a moment to study over the chart on the left-hand side, which designates the load design, capacity, and operating hours, and compare that to the graph on the right so that you can see a visual representation of our cooling load profile for the building. Using traditional sizing methods, the pipe size required to address our flow of 81 gallons per minute at peak load is 2.5 or 3-inch pipe. This is consistent with ASHRAE Standard 90.1, except 3-inch is the minimum pipe size for a constant flow system, but 2.5-inch is acceptable for a variable flow, variable speed system. Since 90.1 only defines the maximum water flow in a pipe, in the case of a variable volume, variable speed system being applied to our example, the designer could choose to use 2.5-inch or 3-inch pipe. So in this instance, what are the operating conditions if a 2.5-inch pipe is selected? We can see by this chart that the head loss would be 4.5 feet per 100 feet and would have a velocity of 5.2 feet per second. Next, we'll look at the operating conditions if 3-inch pipe is selected. We can see that the head loss is 1.75 feet per 100 foot of pipe, and the velocity is 3.5 foot per second. Now, in comparing the operating conditions between the 2.5-inch and the 3-inch pipe, we see that the 3-inch pipe has a lower head loss, but the material first cost will be higher. A factor not previously considered is that the demand for peak cooling will only occur 19 hours per year for this building. Referring back to our graphic of our load profile for our example 4-story office building in Houston, Texas, most of the cooling operation hours occur at less than 50% of the design load. Therefore, when we size the pipe for peak load alone, we're greatly oversizing the pipe a good portion of the time. Recognizing the fact that the peak load occurs so infrequently, one could conclude that the head loss and velocity will be much less than those listed here, 4.5 feet per 100 feet and 5.2 feet per second, because it's a variable volume, variable speed system. Having stated this, even when at these peak values would be considered acceptable. The fact that this is a closed-loop chilled water system makes concerns related to noise and erosion insignificant. Specifying a 2.5-inch pipe is certainly justifiable and may be selected because this saves money in piping first costs, and it requires little to no sacrifice in system life or performance. The hesitancy will likely come from those that design using the equal friction rate method, as it will require a change from what they have done in the past. The best way to make this decision is to consider the system life cycle cost, since ultimately the decision comes down to the financial impact. A free software tool for pipe size optimization is available for download from Energy Design Resources. The software allows a designer to enter the conditions of their system, and it performs an economic life cycle cost analysis for pipe sizing. The program allows for the user to dictate whether they are designing a constant or variable volume system, their utility rates, the first cost of the components, and etc. This software is used to analyze the critical circuit of our example building. The program defaults on unit pricing, utility rates, etc. were used rather than altering them to the specifics of our example. The program recommends the optimum pipe size as well as determines the life cycle cost for the system. As shown here, the life cycle cost is less for the variable volume, variable speed pump system, which can be attributed to the energy savings since its first costs are higher. An item that requires clarification is related to the first costs shown here. In prior slides, we stated that decreasing the pipe size would result in savings in first cost. This is true, but does not show up in the first cost listed here, because the first cost here also includes an increase in system cost to change from a constant volume to a variable volume, variable frequency drive pump. If we were to look at only the piping cost of the variable volume system, this would be much less than the constant volume system due to the reduced pipe size. One thing that should be noted is that the software generic pump performance curves were used in this calculation with an efficiency of 58%. It can be expected that the energy savings using the Magna 3 would be even greater, having an efficiency of 74%. Primarily, we have been discussing new system design in this presentation. Recognizing the opportunity for more retrofit work in the future, one concern is the limitations imposed by ASHRAE Standard 90.1 in regard to pipe sizing. The flow limits applied to pipe based on size are a concern, especially when an existing piping system would like to be reused, but the system capacity needs to be increased to address new loads. There are two options that should be considered. The first is to change the system to a variable volume, variable speed system, which allows for higher flow limits, the same pipe allowed to carry more gallons per minute. The second would be to maintain the same gallons per minute, but increase capacity by increasing the difference between the delivery and return water temperatures, or running the system at a higher delta T. These are just also considerations as we think about ASHRAE Standard 90.1 in regards to the pipe sizing. This presentation has focused on pipe sizing considerations and how this ultimately impacts a system's efficiency. As you invest more time into this topic, you may find the following free resources also helpful. To receive your PDH certificate for this training, please send an email to training-us@grundfos.com. Please confirm your name, the course name, and the date that you've completed this course.